Hi friends, in this video we are going to study about optoelectronics. Optoelectronics means study and application of electronic devices which detect and control light. The important applications of optoelectronic devices as optocoupler and optical fiber communications. Let us see some of the optoelectronic devices: photodiode, laser diode, optical fiber, light emitting diodes and solar cell. Before we enter to the optoelectronics, we must know about Bohr's atom model, energy level, energy band, band gap and formation of p-n junction diode. First of all, we see the Bohr's atom model. All the electrons are revolved around the nucleus in definite orbit. Lower orbit has lower energy, higher orbit has higher energy. When an electron jumps from higher energy to lower energy, it generates photon. The energy of the photon is equal to the difference between the energies of that orbits. In the third point itself, photon, I think it's a new word. The photon is the packet of or bundle of light. It behaves as a particle. Photon can be represented as shown in the figure. A single photon has an energy which is given by E is equal to h nu, where nu is the frequency, h is Planck's constant. Frequency is nothing but c by lambda, that is velocity of light divided by wavelength of the light. This animation will give the clear ideas about Bohr's atom model. First point, that all the electrons are revolved around the nucleus in definite orbit. The second point is, when an external energy is given to an electron in the lower orbit, which has lower energy, it transits to higher orbit, which is higher energy. So, according to this diagram, E1 has lower energy, E3 is higher energy. So, external energy is given to an electron in the lower orbit, it transits to higher orbit. Next point is, when an electron jumps from higher energy to lower energy, it generates photon. That energy of that photon E is equal to E3 minus E2, that is the difference between the energies of the orbits E3 and E2. For our convenience, instead of represent the circular orbits, we consider a straight line as energy level. Lower orbit has lower energy, which is called as ground state, and higher orbit has higher energy, called as excited state. So, according to the figure, E1 is the ground state which has lower energy, E4 is the excited state which has higher energy. Here we see how energy band is formed from the energy levels. Consider a single atom has 4 energy levels. For 2 atoms which also have 4 energy levels. When they are close to each other, due to intermixing of electrons, in the respective level of atoms merge. For solid, the entire atoms made the band. There are two bands formed. Lower band is called valence band. Above the valence band, you can see conduction band. So, due to intermixing of electrons in their energy levels, which constitute a band, the range of energies possessed by an electron in a solid. This is the exact definition of the energy band. Next, let us see what is energy band gap. A gap between valence band and conduction band. In other words, we can say it a gap between higher energy of valence band and lower energy of conduction band. It is expressed in terms of electron volt. The magnitude of the band gap determines the difference between insulators, semiconductors and metals. Based on band gap, how solid is classified into three types. The first one is good conductor, which conducts electricity freely. The second one is bad conductors or insulators, which do not conduct electricity freely. The third one is semiconductor, which have the both properties of good conductor and bad conductors. That means, at low temperature, say absolute temperature 0 Kelvin, it acts as a bad conductor. At high temperature, say room temperature, acts as a good conductor. The examples of semiconductors are germanium and silicon. In all the types of all energy levels are filled with electrons or empty, which do not involve electrical conductor. So, let us see the first figure. Each energy level has occupied by the electrons in the band, that is full band. That band is occupied by electrons. Next, in the case of second diagram, is an empty band, all the energy levels are empty, no electrons present there. But these two are not involved in electrical conduction. Next is the good conductors. You see, valence band and conduction band are just touching together. So, there is no band gap in between valence band and conduction band. Hence, they have always free electrons to conduct electricity freely. Another model of conducting material is overlapped. Here also we cannot see the band gap. So, from this we conclude these two bands look like as if partly filled bands. This is the reason why metals have high conductivity. Example of good conductors are all kind of metals. So, no band gap between valence band and conduction band. Bad conductors or insulators. We can see a large band gap or broad band gap between valence band and conduction band. So, even very high external energy is also unable to promote electrons from valence band to conduction band. Examples of that bad conductors: glass, plastic and rubber. So, there is a wide band gap between valence band and conduction band. Next, semiconductors. We can see a very narrow band gap in between valence band and conduction band. We already studied about the semiconductors are having two properties like good conductors and bad conductors depends on the temperature. So, first case at low temperature. At low temperature, the semiconductors are having the following property. Now, the valence band is full and the conduction band is totally empty. Recall that a full band cannot conduct and neither can an empty band. So, at low temperature, semiconductors do not conduct, they behave like insulators. The example of germanium has a band gap as 0.7 electron volt, for silicon 1.1 electron volt. Next, we are going to study about the semiconductors property at high temperature, that is say room temperature. Let us see how it conducts at the room temperature. When enough energy is supplied to the electron in the valence band, electron can move to conduction band from the valence band. The electrons leaves a missing electron state. That vacant site is called as hole. The hole behaves as positive charge carrier since in the absence of electron. Now, just a recap the classification of solids based on band gap. Good conductors, there is no band gap between valence band and the conduction band. Example, all kind of metals. Semiconductor, there is a narrow band gap between valence band and conduction band. So, lesser than 3 electron volt. For example, germanium, it has 0.7 electron volt. Bad conductors, there is a wide band gap between conduction band and valence band. For example, glass is 10 electron volt. So, more than 4 to 5 electron volt, it will become bad conductor. Among the many optoelectronic devices, we are going to study about LED, that is light emitting diodes, and photodiode. First, let us study light emitting diode, which is known as LED. What is LED? It is a p-n junction in forward bias which converts the electric energy into optical energy. The symbol of LED is, just draw the diode diagram and draw two outward arrows from the junction, which is nothing but symbolical representation of LED. Next, construction of LED. LED consists of a chip which is indicated in the diagram as blue in color, that is p-n junction diode. That material doped with certain impurities to create a p-n junction, but that materials should be direct band gap. The chip is mounted on an anvil. The contacts are made with lead frames. An anode frame, a golden wire is bonded to p-type semiconductor. The cathode frame is connected with n-type semiconductors of the diode. The transparent plastic case encloses the chip area. At the top side, epoxy lens case is designed. So, this is a p-n junction diode which is made up of direct band gap materials, which is more important point here. This is the main difference between the ordinary p-n junction diode and LED. Before we studying about the working of LED, we should know about the indirect band gap materials and direct band gap materials. Have a look on indirect band gap figure. Here E is an energy, K is wave factor, but it is not necessary to explain here, but you can think it as somewhat it is related to the momentum. So, K is momentum, E is energy. When electron in lower energy of conduction band transit to the hole in the higher energy of valence band, here the momentum is conserved. Finally, it generates a heat. So, it happens only in p-n junction diode. So, the indirect band gap materials examples are germanium and silicon. Now, just look at that direct band gap energy diagram. When an electron jumps from the lower energy of the conduction band to higher energy of valence band, it emits a photon. Here you see both conduction band and valence band are having the same momentum value. So, the change in momentum is equal to 0. So, no momentum. During recombination, photon is produced. So, it happens only in LED. The direct band gap materials examples are gallium arsenide, gallium arsenide phosphide, gallium nitride. Thus, the light emitting diode is emitting the light in forward bias, whereas ordinary p-n junction diode in forward bias has not having this property. The main difference is the made up of materials. Now, let us study about the working of LED. Here p-n junction diode is made up of direct band gap materials like gallium arsenide. Now, the circuit is switched on. Electrons are moving from negative terminal of the battery to cathode. At the same time, holes are moving from positive terminal to anode. The electrons in the cathode just push the electrons in the n type. At the same time, the holes in the anode just push the holes in the p type. So, the depletion region, there is a chance to occur recombination of the electrons and holes. During the recombination process, the photons are emitted in forward bias. Thus, the LED is worked. So, during recombination of electrons and holes, photons are generated is the main concept in the working of LED. Let us study about the other optoelectronic device, that is photodiode. What is photodiode? It is also a p-n junction diode in reverse bias. Mind it, in the LED it should be connected in forward bias, mind it. Photodiode is a p-n junction in reverse bias that generates current when photon passes through it. That means that light energy converts into electrical energy. Then the symbolic representation of that photodiode is nothing but just draw the diode diagram and two inward arrow marks towards the junction. Next, we study about the construction of photodiode. PN junction is made with germanium or silicon or germanium phosphate or indium gallium arsenide materials. The middle portion of the top surface is transparent, where the radiation falls through this transparent portion of this photodiode and reach the PN junction diode. Next, we are going to see how it works in reverse bias. PN junction diode is connected in reverse bias. Already depletion region is formed during the formation of PN junction diode. Now, the circuit is switched on. The holes are reached the cathode and the electrons are reached the anode from the respective terminals of the battery. Due to opposite charges, the holes in cathode attracts electron in N type. Simultaneously, the electrons in anode attracts the hole in the P type, so that the more number of ions are developed near junction, and hence the depletion region is also increased. Without radiation, only minority current is produced. This transient current is called as dark current. In this depletion region, neutral atoms are there. When the light is falling on the PN junction, we can say that in depletion region, the electron is dislodged from the neutral atom. And the electron just transit to nearby holes and thereby it reaches the cathode. Since it is connected in the reverse bias, the electrons are attracted by positive terminal of the battery and the holes are attracted by the negative terminal of the battery. In this way, the electron and holes are produced by minority charge carriers. Due to this, the depletion region is decreased, so that the potential barrier also decreased. Now, the applied reverse voltage is greater than that of the depletion region voltage, that is barrier potential voltage. So, the current can easily go through it. For continuous radiation, the electrons and holes pairs are generated and the current is produced. So, the electron just move from cathode to anode. In this way, the current is conducted in the photodiode in the reverse bias. Thus, the photodiode in reverse bias just converts the optical energy into electrical energy. Here the main concept is the photon separates electrons and holes. So, N type electron flows towards positive terminal of the battery, then reach anode and enters P type. This comparative tabulation is for points to remember. So, PN junction diode symbol, the two bias condition. What is the use of that PN junction diode? AC into DC. Light emitting diode, which should be connected in only forward bias, which converts electrical energy into light energy. Uses of LED: So, or aviation lighting, automotive headlamps, advertising, traffic signals, camera flashes. The last one is photodiode, photodiode symbol, and it is working or converting light energy into electrical energy. It is working only in reverse bias. The uses of photodiodes are smoke detectors, medical devices, and infrared remote control devices. Thank you.